Hi, my name is Harlan. Welcome to the Machacon Mechanical Engineering channel. Today, the topic I will discuss is the simple pendulum. A simple pendulum consists of a bob of mass m suspended on a string of length L and swung at an angle of theta radians from the equilibrium position. When the bob is swung theta radians from the equilibrium position and then released, the weight of the bob supplies the restoring force F, which is equal to minus mg sine of theta. This one here. We neglect the mass of the string. The displacement along the arc of motion is S is equal to theta times L. The restoring force is proportional to sine theta and not to the displacement. Applying Newton's law of motion, F is equal to mass times acceleration. But the linear acceleration is equal to the angular acceleration alpha times the length L. So by substitution, we have F is equal to m times alpha times L. So equating this to the restoring force F is equal to minus m times g times sine theta, we have m alpha L is equal to negative m g sine of theta. And let us take note that alpha is the angular acceleration equal to the second derivative of theta with respect to time. So hence, we have m times the second derivative theta with respect to time, t, and L. We have minus mg sine theta. And equation 2.3 above can be simplified as this one here, the second derivative of theta divided by time with respect to time, plus g over L sine of theta is equal to 0. And that's equation 2.4. And that equation, 2.4, can also be obtained using the conservation of energy method, wherein the energy equation is potential energy plus kinetic energy is equal to constant. So it will always be the same. The sum of the two energies, potential and kinetic, will always remain the same throughout the length of the swing, the distance of the swing, anywhere in the point of this on the bob. And the potential energy is PE is equal to mass times gravity, acceleration due to gravity, and length minus length times cosine of theta. And the kinetic energy is equal to 1/2 mv squared, where v is equal to the angular velocity times length. And performing the mathematical operations here, we have 1/2 m times L squared, the first derivative of theta with respect to time, quantity squared. Substituting these values in the energy equation, we have mgl minus mgl cosine of theta, and we have 1/2 ml squared second derivative of first derivative of theta with respect to time, quantity squared, is equal to constant. And taking the derivatives of theta with respect to time t, we have mgl sine theta d theta over dt plus ml squared d theta over dt times the second derivative of theta with respect to time is equal to 0. So this can be simplified by removing, you can remove the mass, 1L, the 1L can be removed here, and the first derivative of theta with respect to time can be removed in this equation. So it will be simplified into this equation here, second derivative of theta with respect to time plus g over L sine theta is equal to 0, which is the same equation as we have discussed previously in the first method. This is a second order, nonlinear ordinary differential equation, which is difficult to solve. But we can approximate it as a linear differential equation of the second order using a Maclaurin series as our solution. And so we will be able to approximate it, and we can get an exact solution for the equation. So the Taylor series expansion of f function of x is given as a function of x is equal to the function of x at x equals 0, the first derivative of x at a times the expression here, x minus a, plus the second derivative of a of the function of x at x equals a, and divided by 2 factorial, x minus a squared, and the third derivative of the function of x at a, and 3 factorial, and we have x minus a cubed, and then the fourth derivative of x at x equals a, and 4 factorial, and x minus a raised to the power 4th, and so on and so forth. So you see the trends here. See, second derivative 2 factorial squared, third derivative 3 factorial cubed, and fourth derivative 4 factorial and fourth. So Maclaurin series expansion is simply a Taylor series expansion of a function of x at a equals 0. So you have function of x equal to the function of x at x equals 0 plus the first derivative of x at x equals 0 times x, and plus the second derivative of x at x equals 0 divided by 2 factorial and x squared. You have the third derivative of the function of x at x equals 0, 3 factorial and x cubed, and you have the fourth derivative of the function of x at x equals 0, and you have here the 4 factorial and x to the fourth. So take note of this trend here. Second derivative, 2 factorial and squared, third derivative 3 factorial and cubed, and fourth derivative 4 factorial and fourth, and so on and so forth. So the Maclaurin series can also be expressed in summation notation. We have summation n equals 0 infinity fn at x, f of x at x equals 0, and factorial x to the raised to the power n. That we will consider that as equation 2.5. Applying this to the sine function of theta will result to sine theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus theta to the 9th over 9 factorial, and so on and so forth. Take note, it alternates in the sign, minus, plus, minus, plus, minus, okay, and plus, okay. So you have theta cubed, 3 factorial, theta to the 5th, 5 factorial, theta to the 7th, 7 factorial, theta to the 9th, 9 factorial. So when the value of theta is small, if this is small, this one is very, very small. And so much more for this one. This is very small. And this one also. So we can remove this. We can approximate sine theta to be equal to theta, therefore. So sine theta is equal to theta when the value of theta is small. It also follows that since theta is small, the restoring force can now be considered directed towards equilibrium with very minimal error, and in this case the motion of the bob will now qualify as a simple harmonic motion. Therefore, equation 2.4 can be approximated by the second derivative of theta with respect to time plus g over L times theta equals 0, which is a second order linear differential equation. The roots of the auxiliary equation are d is equal to plus and minus the square root of g over L times I. And the equation of motion is therefore theta is equal to b sub 1 cosine square root g over L times time t, b sub 2 sine of the square root of g over L times time t. Okay, so you have two arbitrary constants, b1 and b2, and using the initial conditions, you can determine the arbitrary constants b1 and b2. At t equals 0, theta equals theta at 0. So we substitute here. Take note that cosine 0 is 1, sine 0 is 0. So you can equate b1 to theta at theta equals time t equals 0. So substitute it there, and you will now have one arbitrary constant left, and taking the derivatives with respect to time, the first derivative of theta with respect to time, which is equal to the angular velocity, we have this expression here, and so that will be at t equals 0. The first derivative of theta with respect to time is the initial angular velocity, omega at 0. And you have b sub 2 is equal to omega at t equals 0 square root of L over g. So the equation of motion will now become theta is equal to theta at t equals 0 cosine square root of g over L times time t, and this is the omega at sub 0 square root of L over g sine of square root of L over g times time, where this is equal to the natural circular frequency in radians per second, which is equal to 2 pi times the frequency f. And therefore, f can be expressed as 1 over 2 pi square root of g over L. The period t is the reciprocal of the frequency, hence it can also be expressed as capital T period is equal to 2 pi square root of L over g. One of the practical uses of a simple pendulum is to determine the value of the acceleration due to gravity, g, at various locations. So this is the reason why I have included it in my vibration series, mechanical vibration series, because it is very important that we know how to measure the acceleration due to gravity in your locality. Example application. A steel bulb is suspended on a 12-inch string and made to swing freely. It is observed that the bulb makes 108 cycles in 2 minutes. Determine the value of the acceleration of gravity. Applying equation 2.10, F is equal to 1 over 2 pi square root of g over L. So 108 cycles, 120 seconds, 1 over 2 pi g, and L is 1 foot. And so you will be able to solve the value of g. And take note that the mass has nothing to do with it. It has nothing to do with determining the value of g. G will therefore be 31.978 feet per second squared. Thank you for watching, and stay tuned for tutorial number 3 of the mechanical vibration series.